11.5, solubility. So let's define solubility to start out. It's going to be the amount of solute that dissolves in a given amount of water at a certain temperature to make a saturated solution. So how much stuff can we fit into water in order to make a saturated solution? So what if something is soluble? What would that look like? Well, table salt and water. If we stir it up enough, the water's at 25 degrees Celsius, and we had 100 milliliters of water, we could get that table salt to dissolve, and it would disappear. We wouldn't be able to see it anymore. So we know that table salt, just by past experience, we know that table salt falls under the guise of soluble, okay? Because it will dissolve. It will dissolve in 100 mils of H2O at, well, pick a temperature 25 degrees Celsius. It will do that. So we can then say unequivocally that NaCl, yep, is a soluble substance. There are solids out there that are insoluble, and one of those examples is shown in the bottom right hand corner of the video. And this is an example of lead chloride, PB, oops, sorry, I'm back here, lead chloride. And so in the case of lead chloride, it is not soluble, so it will not disappear. It will not dissolve in 100 milliliters of water at 25 degrees Celsius. Instead, it forms this yellowy substance, and that's actually known as a precipitate. A precipitate. So it almost sounds like when it's raining outside or it's snowing, we call it precipitation. This is a precipitate. So a precipitate is a solid that is not soluble or insoluble in a certain solute. That's a precipitate. Okay? So how do we find out like what is soluble and what is insoluble? That's a good question. So we have to go to a chart, and I'm going to hand this chart out in class so that you guys have a reference table. And this chart is going to tell us what is soluble and what isn't soluble. So the first thing we're going to do is look at those two examples we had on the previous page. We're going to look at sodium chloride, so NaCl. And if we go to my chart, I want to look in the leftmost column first. Those are my ions. And I'm going to kind of work my way down that column, and oh, right there, I see chlorine, Cl, and that just happens to be one of the ions that I'm working with. All right, so I want to read this little general solubility rule about Cl. So all chlorides, bromides and iodides, are soluble, with the exception of silver, lead, and mercury. Well, sodium is not silver, lead, or mercury, so that must mean that this stuff is soluble. So I actually don't have to run an experiment. Other people have done it for me, and I can look at this table and tell whether or not a substance is going to be soluble. We had lead chloride as the other example. So again, I use my left column here. I find my chlorine. I read my little blurb, and I notice that there is an exception, and that exception is lead. So because of that, I then can assume that this is going to be insoluble. It will not dissolve in water. And I can do the same thing for pretty much any compound that we're going to come into contact with if I just read my list down here. So if it's a nitrate, if it's a carbonate, if it's a hydroxide, anything that I'm dealing with in this class, I can find within this table. So it'll be a nice reference for us to go ahead and use later on down the road. All right, so let's see. How does solubility look with a chemical reaction? How can we write it in a chemical reaction? Let's look at a double replacement reaction. And hopefully you have that table out on the previous page, so you can try to find you can find the solubilities. So we're going to start with potassium chloride, which is KCl, all right? And we're going to assume that this potassium chloride is dissolved in water. And if you look at the solubility chart, you should see that potassium chloride is soluble. I think all chlorides are soluble with the exception of a couple of things. Potassium is not one of those things, so yes, it can dissolve in water. The top thing, or the top entry in that chart talks about nitrates, and it says all nitrates are soluble. It doesn't matter what's in front, all nitrates are soluble. So that means that the silver nitrate is aqueous. We call that AQ. All right. Now this is a double replacement reaction. So if we remember what that means, a double replacement reaction means that the cations and the anions switch. So I'm just going to underline the cations in red. And so the cations are going to switch partners. It's been a while since we've done this. We'll take this slow. That means the potassium pairs up with the nitrate. And the silver pairs up with the chlorine. All right. Now on the left side, we have indicated what the solubilities are. We've said both of the reactants are aqueous, meaning they're soluble. So let's just write that down here. That means that these two are soluble. All right. On the right side of the equation, we don't yet know if these things are going to be soluble or not. All right. We go to our data table. Well, again, the first thing on that table are nitrates, and it says all nitrates are soluble. So that makes it easy for potassium nitrate. Put an AQ. It shouldn't be below the AQ. In fact, here's what I'm going to do. I'm going to rewrite this so we write it correctly. All right, let's go AQ. There we go. Okay. Plus, the last thing here is silver chloride, AgCl. Now, if you look down on the bottom, we find the chlorines, and one of the exceptions to chlorine being soluble is silver. So that means silver chloride is insoluble. It's a precipitate. So there's a couple of ways to write that. You can either write just a plain old S, and I'll be okay with that. Some people want to make sure that they understand that that is a precipitate, so they abbreviate precipitate PPT, and that would work as well. So either S or PPT. For a double replacement reaction to actually occur, you have to have at least one precipitate to form, or water. If water forms, then the reaction occurs as well. Okay, so it's actually balanced. We don't have to do any balancing with this equation. This is how we actually write a double replacement reaction using our solubility rules. So we have three things in here that are soluble. We have one thing in here that is insoluble. So if you ran this reaction, what you would probably see is in your resulting test tube, here it is, your resulting test tube. Okay, you'd have some liquid inside of there. And then when you ran the reaction, you would see the silver chloride. And the silver chloride, although it's not red, it's white. That silver chloride would start to chunk up, and it would look like a thin, like if you poured milk inside of water, and that milk was insoluble, and it would like sink to the bottom, which I know it doesn't do, but if it would, that's what you would kind of see, this white milky substance that would fall to the bottom of the tube. And that white milky substance at the bottom of the tube is the silver chloride. Now, if we wanted to know something about it, the cool thing about precipitates is that they're real easily filtered. So we could pour our test tube and the precipitate onto some filter paper. The water would fall right through, taking with it the potassium nitrate, so we wouldn't have to worry about that anymore. And guess what would be left on the filter paper? The silver chloride. So we could actually evaluate the silver chloride, see how much there is, see the purity of it, so on and so forth. Okay, so that's solubility.